As we continue here with this section, we're going to see some more ideas about arc length and radians in particular. Basically, we're going to have a real focus here on radians and the definition of radians to help us solve some applications that would really play well in a physics course. Let's get started. So if we remember, let me talk you back through what a radian was. So we're going to establish this definition here. And first of all, what we said, 1 radian is when our arc length, which is represented by S, if S equals R, if it's the same as the radius, then this angle here has created what we'll define as 1 radian. An arc length exactly the same as the radius. Well, suppose it was bigger than 1, and we'd like to know what it is. Well, let's measure that arc length and divide it by whatever the radius is. And that would tell us, well, how many radii, have we walked along the outside? And that would tell us how many radians are in this angle. So again, an arc length of 1 radius makes a single radian. So if the arc length and the radius are the same, then this angle is 1 radian. However, if it's longer than that, all we'd have to do is divide by r to find out how many radians our new angle is. Now, if all that doesn't make sense, here's the point. That the arc length divided by the radius tells us the measure of the radians for the angle. It's just this definition. Now, this is still algebra based, so if I wanted to solve, okay, well, I want to know the arc length. I want to know how far we've walked along the outside of this circle. Well, fine. I'll just multiply both sides by r, and then I would create this formula here. I've essentially swung the r up to the other side. So arc length is equal to the radius times the measure of the angle in radians. Okay, so let's do something with this formula. The first thing here, we're told that we have Mercury is 36 million miles from the sun. Okay, now I don't know where this is going, but I do know this. What they've just told me is a radius. I've got Mercury spinning around the sun, so r is going to be 36 million. I know they just gave me a radius. Now where this is going I don't know, but that's what they've given me. Alright, here in part A. In 1 Earth day, Mercury completes 0.0114 of its total revolution. How many miles does it travel in 1 day? Okay, well, we want to know, they've told us that it goes, well, hold on, let me use theirs here. We know that it's gone part of a revolution. Well, what I want to know is the entire circumference, the entire distance of Mercury's orbit. So what I'm going to do is I'm going to take the formula for a circumference. Isn't the circumference the travel around the outside of the circle? It's the distance that you did if you walked the circle. So let's find the length of Mercury's orbit. So what I'm going to do is I'm just going to plug it into the circumference formula. I know the radius, circumference is 2 pi times r. Okay, well I've got it. So I get about 226 million miles. Now, we know that Mercury has completed a fraction of this revolution in 1 day. Okay, well let's multiply that 226 by the fraction that it's completed, the 0.0114. And we get 258 million miles. Okay. That's our answer to part A here. Now, what it's asking is to determine the... Yeah, so this is in revolutions, but what I want to do is turn this into radians. So what I've got here is, I've got my arc length, which I just figured out. This is how far we went. 2.58 is how far Mercury goes in a single day. And I want to divide that by the radius, which we already knew was 36 million. So I'm dividing arc length by radius, and therefore the radians of this angle, so we're going from this definition again, my measure of my degree must be 0.0717. Okay, let's take another look here. So we want to find the arc length. We're looking for S. And we know that it's related to, hold on, I got to do it like this to make sure I'm doing this right. Okay, that's the original formula, so S is equal to theta times R. Okay, Now, I know the radius. They tell me it's 10 units long. So I know r. Now, I have an angle here, but this is actually not theta. And the reason it's not theta is this definition is created based upon, this is the definition of a radian. That's where this whole formula came from. So I can't use degrees here. So if I want to find this formula, if I want to find the measure of the angle, this formula is about radians. It has to be in radians. So I'm going to take that 215 and I'm going to convert it into radians. Okay, now how would I do that? Well, there's 360 degrees in 2 pi radians. So what I can do here is convert this angle that they gave me into radians, and I'll have everything I need. So hold on, I'm going to do that on my calculator. That doesn't work out perfectly. Hold on. So I've got 430 over 360 pi. So I just multiplied the 2 times 215, divided it by 360. So I'm going to just start reducing this. I could cut it, divide both of them by 10, and I get 43 over 36 pi. Yeah, and I'm going to just leave it at that. Okay, so I now have the measure of the angle. It's now in radians. That's what I wanted. And I know my radius is 10. So I've got everything I need to find the arc length. It is going to be 43 pi over 36 times 10. Now you could crunch this down and get your actual number if you wanted, but I'm just going to leave it as that. Okay, now here they're deriving for us the area of a sector. An area of a sector is a slice of pizza. So if we have an entire circle, that would be as if we'd gone all the way around. And a sector is just like one slice. We sliced up the pizza into pieces. Now the area of a circle is pi r squared. Well, if we only have a portion of it, this represents the fraction of the whole that we have. We don't have all of the pizza, we only have a fraction. So if I multiply the percentage that I have times the entire area, then I would get the area of just my little piece. So the entire area of the formula is here. This is my percentage. How much of the entire circle is my slice? If I multiply those together, I would then get the area of just my section. Doing a little deriving, and we come up with this formula here. So the area of a sector is going to be 1/2 the measure of the angle in radians times r squared. Now remember here, we need the measure of this angle and r squared. We need this angle to be in radians. Now I don't know if I've said this somewhere else, but let me do a tangent here real quick. Oops. So this is the definition of the measure of this angle. It's s over r. Now do you see, radians actually have no real unit, because we would measure the radians, whatever unit we measured the radius, it's going to be the same unit that we would measure the arc length on the same side. Like, what distance are we measuring this curve in, and what distance are we measuring the radius in? Well, you're going to divide them. And so those units, so suppose they were both in centimeters. Well, if they're both in centimeters, when you divide them, it would drop out. So just a quick tangent here, radians don't have a unit because you're dividing the unit away. Okay, so here we've got our formula, which was just derived on the last screen. We've got our formula for the area of a slice of pie, for a sector, an area, a section of a circle. Okay, so let's talk about some problems here. So let's see, what have they given me? So what they've given me here is I've got a radius. So what they're saying is this sprinkler can reach 20 feet. So it's hitting 20 feet, so that's my radius. And it can rotate 30 degrees. Now here's the problem. That 30 degrees is not going to help us because we have to be in radians. This whole process has to be in radians. All of these formulas are based on the definition of a radian. So I need to convert this, first of all, by multiplying it by 360 degrees over 2 pi. That's how I would convert between the two systems. well, they've done the same thing. They used pi over 180, but that's the same equivalent thing, just simplifying that by 2. Okay, so multiply that out, we get pi over 6 radians. So those would cancel down and get you 6. So pi over 6, that's the measure of our angle. Okay, now I didn't even know what they were asking. We want the area of the sector. Now we have everything we need. We've got our radius, we've got an angle that's in radians, because that's what the formula is based on. So we're going to plug that in. 1/2 pi over 6 times the radius squared, and here's the area of our sector. And again, notice, we don't have units on the radians, but we have a unit on the radius. It's 20 feet. So when we calculate this, we're going to get feet squared for our area. Okay. All right, so here's what we've got here. They tell us our radius. Now, I don't even know what the question's about yet. I'm just going to start writing down what they've given me. I know I've got a radius of 400 meters. And water restrictions allow her to do 150 square meters a day. So what is that? That's an area. Because they're telling me square meters, I've got 150,000 meters squared. There's my area. Here's my radius. Okay, so they want me to find the angle that this system can cover. Well, I've got area and I've got radius, so they must be asking me to do this. 1/2 theta r squared. Okay, well, I have everything but the theta, and that's what they wanted. They wanted the angle. So I'm going to put these things in. I've got 150,000 equals 1/2 theta times 400 squared. Now I'm just going to crunch this on my calculator. I'm going to divide both sides by 2, and I'm going to get 300,000. I'm going to divide by 400 to the second. And I get theta is 1.875. So that's 1.875 radians. That is the measure of the angle that she could cover in order to do this 150,000 square meters. Okay, we've got one last formula we're going to do, and then we have a couple odd and kind of questions to follow it. We have two different ways to measure speed. And the way this makes the most sense to me is if we were, I don't know if you've ever run track. I wasn't very good, but I did run track. You know how they do this? They have the different lanes on the outside of the track. Now, if you had two runners starting here, one person on the inside of the track and one person on the outside, we could first measure just their speed. How fast are they going? And as they're running, we could say, okay, well, how far, well, this is an oval here. I should have done a circle, but how fast are they running would be how far, what's the arc length that they've covered? Let me change this to a circle. So a track isn't really a circle, but okay, I've got the two runners, one in here. So how, what is the arc length of the circle that they've covered? And then what was the time in which they did this? So in other words, what's the distance that they've covered divided by time? Well, that's velocity. That's what we've seen anytime we've studied speed in the past. How far have we gone? Well, that's an arc length because you're running in a circle. And you just divide it by the time. And that would tell you how fast you're going. Now, but there's another type of speed called angular speed. And it's a very different idea. I mean, they're obviously closely related, but it's this. Suppose you had, what are those, I don't know what you call those things that the movie studio does where they clamp it down when they say action. Well, you have one of those. You've got this angle here that you're, instead of slapping it closed, you're opening it up. So you keep opening this angle as the runner goes. Well, what we're going to do is we're measuring how fast we're opening up this angle. So how fast is the runner going from these distances? But I don't care about the feet he's actually traveled on the ground. I want to know how fast the angle has opened. I'm literally grabbing the angle and I'm pulling it open. And you could open that at different speeds. I could open it very quickly, or I could open it very slowly. And so what we're going to do is we're going to say, okay, angular speed is how fast we open this angle, how fast we rotate. So what we would do is, okay, well, what was the angle that we covered, but how fast did we open it? So in other words, we're checking how fast we are rotating through an angle. So they're obviously closely related, but velocity is the arc length. It's the distance we're traveling on the ground. But angular velocity, angular speed, is how fast is the angle growing open. And we would divide that by time. Now, on this screen, they're doing a little deriving to show the connection of several formulas that we had. But what we're getting at here is that they're going to derive that velocity has a special relationship with this angular rotation. So here's what we have. We've got angular speed. How fast am I opening up that angle? Then we have just good old-fashioned velocity, linear speed. How far am I actually traveling a distance on the ground? And this is saying they're connected. Well, how are they connected? Let me show you an idea to help you see this. So this is where my track idea at the beginning comes in. If you have two runners, one of them's running on the outside of the circle and one on the inside. If they get to this, suppose they both get to the same location at the same time. So the runner on the outside is here, the runner on the inside is here, both after, I don't know, a minute or something like that. You see, they're not actually the same speed. The runner on the outside is faster because he's had to cover more ground. And so my point here is velocity is directly related to the radius that you're covering. If you're covering a larger radius, you must be going faster. So these two guys are covering the same ground, but the guy on the outside is faster because his radius was longer. So I don't know if that's helpful to you or not, but here's all we need to see at the end of the day. There is a relationship between that linear speed and the angular speed, and we can define it here, which was derived on the last slide. The linear speed equals the radius times the angular speed. Okay, so let's do, I think we have just a couple more questions here. We'll talk about how this ties together. So we want to find the angular speed in radians per second. Okay, so yeah, what we've got here is we have the angular speed, but it's in rotations. And so we need to convert this. So what they have for us is they've told us that the angular speed, we have one rotation. Well, one rotation is a circle, but we need this angle. So we need this. Angular speed is the degree that you've covered in radians divided by the time. Well, they're telling us we've gone one rotation in 5 seconds. But a rotation doesn't fit this definition. Once again, we need to be in radians. So instead of saying one rotation, we're going to say we went one time all the way around a circle, which is 2 pi. So again, the problem is we have the formula. We want angular speed, and we have rotation, but that's the wrong word. We need this to be about radians. So we convert it to 2 pi because that's a radian. That's in radians, and we divide it by the time, 5 seconds. Okay, what do we got here? All right, so once again, we have 45 rotations in 1 minute. All right, that's great, but that's not angular speed. Angular speed has to be in radians, and they want radians per second, so we've got some converting to do. So we have the wrong units. Rotation, we have a rate here. We've got rotations per minute, but we've got to make some changes. So do you remember this idea? We're going to cancel the words here. So what I'm going to say is one rotation is 2 pi radians. Do you agree with that conversion? And then what you can do is the word rotation cancels with the word rotation down there. Now, that would solve the problem. If you multiply across, you're now going to have radians as the word on the top. But on the bottom, we're in minutes. We need to fix that as well. We know that 1 minute is 60 seconds. Well, that's what we want to end up with. When we're done, the only units we're going to have left, minutes will cancel with minutes, and I will now have radians divided by seconds. Okay, so I'm going to multiply across the top. I've got 90 pi over 60, and this is now radians per second. So you could reduce this, you can get the actual number on your calculator. So it's giving 9 pi over 6 or 3 pi over 2, just reducing it. Divided both by 10, I saw it was still divisible by 3. So 3 pi over 2 radians per second. So this problem gave us something that appeared to be the speed of rotation. But we need to measure angular speed in radians per second. So we converted. Okay, so we have another similar problem here. So I'm going to write down what I feel like they've given me. They tell me that a wheel has a 28-inch diameter. Now, I don't ever need diameter. What I need is radius. So I know that my radius then is 14 inches. Okay? Now, I also have revolutions per minute. I've got 180 revolutions per minute. Now, that is not angular speed. So we're going to have to do some conversions. So let's do it. I've got 180 rotations per minute, but I want to turn this into an angular speed. So I'm going to turn, there's one rotation is 2 pi radians. Well, and do we want to leave it in minutes? Yeah, they wanted, they didn't tell us to convert us. So last time it told us to convert into seconds, but all we need to do is convert into radians. So we got it. Okay. Now we want the speed the bicycle is traveling down the road. Now, you're catching this. What we just found is, I found theta. I have found angular speed, but they want linear speed. They want the speed that the bicycle is traveling down the road. That's velocity. That's good old-fashioned linear speed. Well, we can convert this because we know v equals r theta. I have r, it's 14. I've got theta, it's 360 pi. So we plug those in, and here is our linear speed. So we converted our rotational speed, and so it was in the correct units, so it was in radians. And then we're using v equals r theta to get the linear speed. Okay, I got one last question here. So what do we got? So we're looking for linear speed. So we're looking for v. Now let's see what we've got. The Earth is rotating. So the Earth is rotating at 0.25 radians per hour. So 0.25 radians per hour. Now that's everything we need for angular speed. 0.25 radians per hour, that's an angular speed. All right. Now, we want to find a linear speed. So I'm going to use v equals r theta. Okay. So the only trick here is that the satellite, so we've got the Earth here, and the satellite is above it. We need the radius to get to the satellite, but they've just kind of hidden it. If we're 242 above the Earth, and the Earth has a radius of 6378, we need to add these two up in order to get the entire radius. Do you see what I'm saying? We have the radius of the Earth, and then we have how high we are above the Earth. Well, the satellite is 6378 plus 242 above the Earth. Now, I'm lazy, and I'm not going to do the addition myself. I'm going to let my calculator do that for me, and so my radius is going to be 6620. All right, so now we have everything we need. We've got the angular speed, we got the radius, so let's find the velocity. Now multiply that by 0.25, and we get a linear speed of 1655 kilometers per hour. Okay, so the hard part is knowing what you're looking for. I saw they're giving me, this is an actual angular speed. It's in radians already and per hour. So I had angular speed right here. Now, I'm looking for linear speed, so I knew I was using this formula. The only thing that was tricky was the radius. Here was the radius of the Earth, and here is how far above the Earth we are. So it's extended the radius a little farther. So the radius for the satellite is 6620. I crunch those, and now I have linear speed. Okay, there's a lot there, real physics kind of based section, but hopefully that makes sense. What we're looking here is basically applying the idea and the definition of radians into different contexts.